Hello there, and welcome to Sleep Science Daily. I'm so glad you found your way here tonight. Maybe you had a long day, or maybe you're just the kind of person who likes to fall asleep thinking about something larger than the day you just had. Either way, tonight's journey is for you. There's nothing you need to do but rest, because tonight we're not going far. We're staying in this solar system. We're visiting the one thing that has been present every single day of your life that you have never once truly seen. Tonight is about the sun. Not the bright thing in the sky, the real one. The nuclear furnace, 4.5 billion years old, burning at 15 million degrees, that made the air you're breathing and the warmth in your body and the world you live on, the star you were born under, the one still burning right now on the other side of the earth as you drift towards sleep. If these quiet journeys help you rest, consider subscribing to Sleep Science Daily, one sleepy soul at a time. Let your body soften. Let your breathing slow. Let's begin. The sun is not on fire. This is the first thing, and it changes everything about how you picture it. When we say something is on fire, we mean it is burning, reacting with oxygen, consuming fuel, producing heat and light, the way a candle or a campfire does. But the sun has no oxygen to burn with. Space is a vacuum. There is nothing to feed a flame of that kind. What the sun is doing is something far stranger and far more powerful than fire. At its core, hydrogen atoms are being crushed together under unimaginable pressure and heat until they fuse, merging into helium and releasing energy in the process. Not the energy of a chemical reaction, the way burning releases energy. The energy of matter itself being converted. The energy locked inside the nucleus of an atom, the deepest reservoir of energy that exists in the physical world. This process is called nuclear fusion, and we have never successfully replicated it on Earth in a controlled, sustained way. The thing that has been warming your face on summer mornings your entire life is powered by a process humanity has not yet mastered. Every second, the sun converts 600 million tons of hydrogen into helium. 600 million tons. Every second. Not every hour, not every day. Every second. Without pause, without slowing. For 4.5 billion years. The numbers are so large they stop meaning anything if you try to hold them directly. So instead, just hold this. The energy released in a single second of the sun's fusion is more than all of humanity has ever used across the entire history of civilization. Every fire ever lit, every engine ever run, every power plant ever built, all of it added together is less than 1 second of the sun. And the sun has been doing this for 4.5 billion years. The sun is 4.6 billion years old, the same age, roughly, as the Earth. They formed together, born from the same collapsing cloud of gas and dust, the same ancient material drifting through the galaxy. The sun gathered most of it, pulling the majority of the mass toward its center. What was left, the small fraction that didn't fall into the sun, swirled into a flat disk around it, and from that disk, the planets slowly assembled themselves. The Earth was not separate from the sun's birth. It was part of the same event, the same cloud, the same moment of collapse. The sun and the Earth are siblings in the truest sense of the word, made from the same material, born at the same time, still traveling together through the galaxy 4.5 billion years later. The cloud that formed the sun did not come from nowhere. It was the remnant of something older, a previous star, or perhaps several, that had lived its life, exhausted its fuel, and died. In dying, it scattered its contents into space. Heavy elements forged in its core over millions of years, carbon, oxygen, silicon, iron, released into the galaxy to drift and cool and eventually gather into new clouds. The Sun formed from those remnants. It is, by the best estimates, a third-generation star, meaning the material inside it has already been through at least 2 previous stellar lifetimes before this one. The iron in the Earth's core, the silicon in the rocks, the carbon in every living thing, all of it was forged in stars that died before the Sun was born. You are not just made of stardust. You are made of very old stardust. The Sun is classified as a yellow dwarf. Not because it is yellow from space. The Sun appears white, not yellow. The yellow color we see from Earth is a product of the atmosphere, which scatters certain wavelengths of light more than others. And not because it is small, the Sun is, by human standards, enormous. It is a yellow dwarf only by the standards of stars. In a universe where stars come in sizes that make the Sun look modest, it is a middle-aged, middle-sized, ordinary star. Unremarkable in almost every way that astronomers use to classify stars. And yet, from where we stand, there is nothing ordinary about it. From where we stand, it is the center of everything. The Sun contains 99.86% of all the mass in the solar system. Everything else, Jupiter, the largest planet, larger than all the other planets combined, Saturn, with its rings, the rocky inner planets, Earth, the Moon, every asteroid, every comet, every speck of dust drifting through the space between planets. All of it together makes up the remaining 0.14%. The solar system is not a collection of planets with a star in the middle. It is a star with a small amount of leftover material orbiting around it. The planets, including the one you are lying on tonight, are a footnote in the Sun's story. 1 million Earths could fit inside the Sun, not side by side in a line packed together, filling its interior. 1 million of the planet you live on, with all its oceans and mountains and atmosphere and everything that has ever lived on it, could fit inside the Sun with room to spare. It is difficult to know what to do with a number like that. The mind reaches for it and comes back empty. So instead, let it simply rest there, somewhere beneath thought, the quiet fact of it. That the world you know, the entirety of human experience, every civilization and every life and every story ever told on this planet, all of it exists inside a margin of error in the size of the nearest star. If the Sun were the size of a front door, the Earth would be a coin placed 27 meters away. A coin, not a basketball, not a tennis ball. A coin, small enough to cover with a thumb, far enough away that you would have to walk the length of a classroom to reach it from the door. And yet, across that distance, scaled back up to 150 million kilometers, the Sun's light and heat reach us with enough energy to fill the atmosphere with warmth, drive the weather systems that water the continents, power the photosynthesis that fills the air with oxygen, and warm the skin of every living thing on the surface of that tiny coin. Distance, it turns out, is no obstacle to a star. The Sun is traveling through the galaxy. It does not sit still at the center of the solar system while the planets circle around it. The whole system, Sun, planets, moons, everything is moving together through the Milky Way at about 230 kilometers per second, orbiting the galactic center in a path that takes roughly 225 million years to complete. One full orbit around the galaxy is sometimes called a cosmic year. The last time the Sun was in this part of its galactic orbit, the dinosaurs had not yet appeared on Earth. The sun you see in the sky is not where it was when the dinosaurs saw it. It is not where it will be when whatever comes after us looks up at the sky. It is moving, always moving, carrying everything with it through a galaxy that is itself moving through the universe. Nothing in the cosmos is standing still, including the star at the center of your world. The light reaching Earth from the sun right now left the sun 8 minutes ago. 8 minutes. Not years, not centuries, 8 minutes. Compared to the vast timescales of the universe, this is nothing. The light from the nearest star beyond our sun takes 4 years to arrive. Light from distant galaxies takes billions of years. 8 minutes is almost intimate by cosmic standards. A brief commute across the inner solar system. And yet, in those 8 minutes, something extraordinary happens. Energy produced in the core of the sun, born from the fusion of hydrogen, carried outward through layer after layer of the sun's interior over 100,000 years, crosses 150 million kilometers of empty space and arrives here. Arrives at this planet. Arrives at the leaves of trees, the surfaces of oceans, the skin of every living creature outdoors. Arrives and becomes life. Nobody has ever been inside the Sunday. No probe, no instrument, no signal of any kind has ever penetrated its interior and returned with direct information. The surface alone is 5,500 degrees hot enough to vaporize any material we have ever created. Below the surface, the temperatures climb steeply. By the time you reach the core, you are at 15 million degrees. There is no technology that exists or could exist that would survive the journey. Everything we know about the inside of the sun, we have inferred. From the way it vibrates, from the light it produces, from the particles it releases. From mathematics applied to physics, we have tested in laboratories on Earth and then extended carefully to conditions no laboratory could ever replicate. We know the sun's interior, the way a doctor knows the inside of a body, without opening it through signals, through patterns, through the logic of what must be happening, given what we can observe from outside. And what we have inferred is extraordinary. At the core of the sun, the temperature reaches 15 million degrees Celsius. 15 million degrees. The surface of the sun, the part that produces the light we see, is about 5,500 degrees. Hot enough to blind you if you look directly at it. Hot enough to vaporize metal. And yet the surface is less than 1/10% as hot as the core. The core is where the fusion happens. Where hydrogen nuclei moving at speeds, their temperature demands collide with enough force to overcome the natural repulsion between positively charged particles. Where 4 hydrogen nuclei, in a series of steps, fuse into one helium nucleus, and where the slight difference in mass between what went in and what came out is released as energy, the energy that will, eventually, become the light entering your window in the morning. A photon of light takes 100,000 years to travel from the core to the surface. This is one of the stranger facts about the sun, and one of the most quietly beautiful. The distance from the core to the surface is about 700,000 kilometers. Light, traveling at 300,000 kilometers per second in a vacuum, could cross that distance in a little over 2 seconds. But inside the sun, light does not travel in a straight line. It cannot. The interior is so dense, so packed with particles, that a photon travels only a tiny distance before colliding with something and being absorbed, re-emitted in a random direction, and sent on its way again, and again, and again. Billions of times. Slowly, erratically, the energy works its way outward, not in a straight line, but in what physicists call a random walk. bouncing through the interior of the sun like something that cannot find its way out of a very crowded room. It takes, on average, 100,000 years. The light warming your skin on a summer afternoon began its journey in the core of the sun before modern humans existed, before agriculture, before language as we know it, before anything that would be recognizable as civilization. It spent 100,000 years making its way to the surface and then crossed 150 million kilometers of empty space in 8 minutes. 100,000 years inside, 8 minutes outside. The sun has layers, like an onion. If an onion were 1.4 million kilometers across and made of plasma at millions of degrees, at the center is the core, the fusion engine, the source of everything. Around the core is the radiative zone, where energy moves outward slowly, passed from particle to particle in the endless series of absorptions and re-emissions that produces the 100,000-year journey. Further out is the convective zone, where the plasma is hot enough and the conditions right for a different kind of energy transport. Convection, the same process that makes soup bubble in a pot on a stove. In the convective zone, hot plasma rises toward the surface, cools slightly, becomes denser, and sinks back down, only to be heated again and rise again. Giant columns of rising and falling plasma, each one larger than the entire Earth, cycling continuously. From above, the surface of the sun shows the tops of these columns as a texture called granulation, a constantly shifting pattern of bright, rising regions surrounded by darker, sinking edges, like a living mosaic, never still. The surface of the sun is called the photosphere. It is where the light we see actually originates the layer thin enough that photons can finally escape rather than being immediately reabsorbed. It is about 500 kilometers thick, which sounds substantial until you remember the sun is 1.4 million kilometers across. The photosphere is, in relative terms, thinner than the skin of an apple. At 5,500 degrees, it is the coolest part of the sun's visible structure, and it is the part we have studied longest, mapped most carefully, watched most closely. Sunspots mark its surface. Solar flares erupt from it. The granulation pattern covers it in constantly moving texture. It is the face the sun shows to the solar system, and it has been showing that face, largely unchanged, for 4.5 billion years. Above the surface, something unexpected happens. You would expect the sun to get cooler as you move away from it, the way a fire is hottest at its center and cooler at its edges. The photosphere follows this logic, but the layer above the photosphere, the chromosphere, is hotter, and the layer above that, the corona, the sun's outer atmosphere, is hotter still, by a factor of hundreds. The photosphere is 5,500 degrees. The corona reaches 1 to 3 million degrees. Why the corona is so dramatically hotter than the surface directly below it is one of the great unsolved mysteries in solar physics. It defies intuition. It defies the simple logic of distance from a heat source. Decades of observation, entire satellites dedicated to studying it, and the question remains genuinely open. The corona is doing something we do not yet understand. The nearest star, the most studied object in astronomy, and it is still keeping secrets. Every second, 4 million tons of matter in the sun are converted into pure energy. Not burned, not consumed in a chemical reaction. Converted, transformed, from mass into energy, following the most famous equation in science. A tiny fraction of the mass that goes into each fusion reaction does not come out the other side. It becomes energy instead. And because the speed of light is so large, Even a tiny amount of mass produces an enormous amount of energy. 4 million tons per second, every second, without pause. To picture 4 million tons, imagine every car on every road in every country in the world, and then multiply that by several times. That much mass, every second, vanishing into energy, into light, into the warmth on your face in the morning, into the food on every table that has ever been set on this planet. The sun produces energy through a process called the proton-proton chain. It begins when two protons' hydrogen nuclei collide with enough force to fuse. Through a series of steps involving different particles and different reactions, 4 protons are eventually combined into one helium nucleus. Along the way, energy is released as gamma rays, and small particles called neutrinos are produced. The neutrinos are worth pausing on. They interact almost not at all with ordinary matter. They pass through the entire body of the sun as if it were not there, emerging in an instant, traveling at nearly the speed of light, crossing space in all directions. Right now, as you lie still, trillions of neutrinos produced in the core of the sun are passing through your body every second, through the bed, through the floor, through the earth itself, without stopping, without slowing, without leaving any trace. The sun is passing through you, in a sense, right now, quietly, without asking permission. The sun is middle-aged, 4.5 billion years old, with roughly 5 billion years of hydrogen fuel remaining in its core. It is, by stellar standards, in the prime of its life, settled, stable, burning steadily, producing consistent energy without dramatic fluctuation. This stability is not accidental, and it is not permanent, but for now, for the span of time that includes all of human history and all of human future that we can meaningfully imagine, the sun will burn exactly as it burns tonight. Steady, patient, indifferent to the small lives unfolding on the small planet it warms. There is something oddly comforting about this. The sun was here before anything you know existed. It will be here long after anything you can imagine has passed. Tonight, as you rest, it is burning as it has always burned on the other side of the earth, warming the morning that is already arriving somewhere else, patient and constant in the way only a star can be. Every photon of sunlight begins its life as a gamma ray, not visible light, not the warm, gentle brightness that fills a room on a clear afternoon. A gamma ray, the most energetic, most penetrating form of radiation that exists, produced in the core of the sun during fusion, carrying an amount of energy that would be lethal to any living thing at close range. But by the time it reaches you, it is nothing like that. In its 100,000-year journey through the sun's interior, that original gamma ray is absorbed and re-emitted billions of times. Each time it is re-emitted, it loses a little energy. It shifts from gamma ray to X-ray, from X-ray to ultraviolet, from ultraviolet to visible light. By the time it finally escapes from the surface, most of it has become the ordinary, golden, life-giving light that fills the sky each morning. The sun takes its most violent energy and transforms it over 100,000 years into something a flower can use to grow. Sunlight travels at 299,792 kilometers per second. This is the speed of light, the fastest speed anything in the universe can move. Not approximately, not close to. Exactly that speed, to the limit of our ability to measure it. In 1 second, a photon of sunlight could circle the Earth 7.5 times. In 8 minutes and 20 seconds, It crosses the 150 million kilometers between the Sun and the Earth, a distance so large that if you drove it at highway speed without stopping, the journey would take more than 170 years, 8 minutes and 20 seconds. That is how long ago the light in this room, if any light remains, left the Sunday. That is how long ago the warmth that stayed in your skin from today's sun exposure was still inside a star. By cosmic standards, the Sun is practically next door. By any human standard, it is so far away that its light, traveling at the maximum speed the universe allows, still takes the better part of a quarter hour to arrive. If the Sun suddenly disappeared, we would not know for 8 minutes. This is not a comforting thought, exactly, but it is a quietly fascinating one. The light we see when we look at the Sun is not the Sun as it is now. It is the Sun as it was 8 minutes ago. Everything we observe in space is the past. The further away something is, the further back in time we are seeing it. The Sun is our nearest example of this, our most intimate reminder that looking outward is always looking backward. In 8 minutes, a great deal can happen. But for now, the Sun is there, 8 minutes away, burning as steadily as it has for 4.5 billion years, as far as light reaching us tonight can tell. All the food you have ever eaten ultimately came from the Sunday. Every meal, every bite, every calorie that ever became energy in your body. Trace any food back far enough, and it leads to sunlight. Plants use sunlight to convert carbon dioxide and water into sugar into stored energy. Animals eat those plants, or eat animals that ate those plants, or eat animals that ate animals that ate those plants. The chain is sometimes long and sometimes complex, but it always ends in the same place. A photon leaving the Sunday, crossing 150 million kilometers of space, hitting a leaf, being absorbed, being converted into chemical energy that will eventually, through a series of steps we call the food chain, become the warmth inside a living thing. The warmth inside you right now, as you lie still, that is sunlight, transformed and stored and carried here through the biology of every living thing that came between you and a leaf in sunlight. But sunlight, at its origin, the sun, in a form your body can use. Every calorie you have ever consumed was once a photon. It is worth sitting with this for a moment. Not as a scientific fact to be filed away, but as something to actually feel, if only briefly. The energy your heart is using right now to beat. The energy your lungs are using to breathe. The energy your brain is using to process the words of this story and let them carry you towards sleep. All of it, traced backward, is electromagnetic radiation that left a nuclear furnace 150 million kilometers away. The sun is not just warming the outside of your life, it is powering the inside of it. Every thought, every movement, every heartbeat running on sunlight. The coal and oil that powers most of human civilization is stored sunlight, not metaphorically, literally. Coal is the compressed remains of ancient plants, trees, and ferns and mosses that grew hundreds of millions of years ago, using sunlight to build their tissues, and then died, and were buried and compressed over geological time into the dense carbon we burn today. Oil is the compressed remains of ancient marine organisms. Tiny creatures that lived in ancient seas, built their bodies from sunlight-powered chemistry, died and sank, and were slowly transformed by heat and pressure into the fuel we pump from the ground. When we burn coal or oil, we are releasing sunlight that was captured hundreds of millions of years ago. We are burning ancient summers, ancient forests, ancient oceans full of ancient life, all of it ultimately powered by a star that was younger then but otherwise much the same as it is tonight. The light that warmed a Carboniferous forest 300 million years ago may have heated a room in a house you have lived in. The sun's energy has a long memory. The warmth you feel in direct sunlight is infrared radiation, not visible light, not the part of sunlight you can see. The warmth on skin in sunshine comes primarily from infrared, a form of electromagnetic radiation with wavelengths just beyond the red end of the visible spectrum. Your eyes cannot detect it, but the nerve endings in your skin can, translating those wavelengths into the sensation of warmth that is one of the most universal human experiences. Every time you have ever stepped into a sunny spot on a cold day, every time sunlight through a window has warmed your face while the rest of the room stayed cool, that was infrared radiation from a nuclear fusion reaction, 150 million kilometers away, crossing space at the speed of light, interacting with the molecules of your skin, and producing a sensation your nervous system translates as warmth. The sun reaches across 150 million kilometers and touches you, and what you feel is warmth. The blue sky is sunlight, not reflected light, not a separate thing from the Sunday. The blue of the sky on a clear day is what happens when sunlight enters the atmosphere, and the shorter wavelengths, the blue ones, scatter more than the longer wavelengths when they strike gas molecules. The blue light bounces in all directions, filling the sky. The longer wavelengths, the reds and oranges and yellows, pass through more directly, concentrating in the direction of the sun itself. This is why the sky is blue everywhere you look, not just near the Sunday. The blue has been scattered across the entire dome of the atmosphere. You are not looking at a surface, you are looking into a sea of scattered sunlight, spread in every direction by the air above you. The sky is the sun, dissolved into blue. And the colors of a sunset are the same light, doing something different. When the sun is near the horizon, its light travels through a much longer path of atmosphere to reach your eyes than when it is overhead. The blue wavelengths scatter away before they arrive. What remains is the red, the orange, the gold, the longer wavelengths that survive the longer journey. A sunset is not a different kind of light. It is the same sunlight that filled the blue sky all day, arriving now from a low angle, stripped of its blue by distance through air, leaving only the warm end of the spectrum. Every color you have ever seen in the natural sky, the deep blue of midday, the pale blue of morning, the gold of late afternoon, the red and orange of a sunset, is sunlight. The same light, changed by the angle of arrival, the length of its path through air, the time of day. A single source, producing an endless variety of colors across the hours. The sun paints the sky differently every hour of every day, and it has been doing this for 4.5 billion years. Without the sun, the Earth would freeze within weeks, not gradually, over millennia. Within weeks, the oceans would begin to cool. Within a year, the surface temperature of the planet would average around -18 degrees Celsius. Within a few years, the oceans would begin to freeze from the surface down. The atmosphere would begin to collapse as gases cooled and fell. The warmth that supports every ecosystem, every weather system, every living process on this planet, all of it comes from the sun, and without it, the Earth is simply a cold rock in the dark. The thin layer of life covering this planet, the forests and oceans and cities and fields, exists in a narrow band of warmth produced by a star 150 million kilometers away. That distance feels enormous, but from the perspective of what the sun does for us, it might as well be in the next room. The sun is the reason this planet is anything other than silence and ice. The sun is not still. We tend to picture it the way it looks from Earth, a steady, unchanging disk of light, reliable and constant, rising and setting with the same quiet dependability it has always had. But that picture is the view from very far away, through an atmosphere that blurs and softens everything. Up close as any instrument we have ever sent has gotten, the sun is restless, churning, active in ways that have real consequences for the planet it warms. The surface is never the same from one moment to the next. Plasma rises and falls in giant convective columns. Magnetic fields twist and tangle and occasionally snap. Energy that has been building for days or weeks is suddenly released in a fraction of a second. The sun is not a lamp, it is a living system, dynamic and unpredictable in its details, even if it is steady in its long-term output. Getting to know the sun means letting go of the image of something calm and fixed. It means accepting something more interesting, a star in constant motion, doing things we are still learning to predict. Sunspots are regions where the sun's magnetic field breaks through the surface. They appear as dark patches on the photosphere, darker than the surrounding surface, cooler by about 1,500 degrees, and surprisingly structured in their behavior. They are not random. They appear in pairs, connected by magnetic field lines that loop above the surface. They tend to form at certain latitudes. They move across the surface as the sun rotates, and they follow a pattern. The word dark is relative here. A sunspot is around 3,500 degrees Celsius. If you could somehow remove a sunspot from the sun and place it alone in the sky, it would shine brilliantly, far brighter than the full moon. It appears dark only because it sits against a background of 5,500-degree plasma. Against that backdrop, 3,500 degrees looks like shadow. The number of sunspots follows an 11-year cycle. Every 11 years, give or take, the sun moves through a complete cycle of activity from solar minimum, when sunspots are rare and the surface appears relatively calm, to solar maximum, when sunspots are abundant and the sun is at its most active, and back again. This cycle has been observed and recorded for centuries. It is one of the most reliable patterns in the solar system, not perfectly regular, not clockwork precise, but consistent enough that we can predict, in broad terms, where in the cycle the sun currently sits. Right now, the sun is in a cycle. It was in a cycle when your grandparents were born. It was in a cycle when the first humans looked up at the sky and wondered what the dark patches on its surface meant. The 11-year rhythm has been running for as long as we can see back in the solar record, and it will likely keep running for billions of years to come. The sun has its own seasons. They are just much longer than ours. Solar flares are sudden explosions of energy from the sun's surface. They happen when the magnetic field lines above a sunspot region become so tangled and stressed that they snap, reconnecting in a new configuration and releasing an enormous burst of energy in the process. The release is almost instantaneous. In a fraction of a second, energy that has been building for days is released as radiation across the entire electromagnetic spectrum. Radio waves, visible light, ultraviolet, X-rays, and gamma rays, all pouring outward from the eruption site simultaneously. The energy released in a large solar flare is roughly equivalent to billions of nuclear bombs detonating at once, not over minutes or hours, in seconds. The sun produces events of this magnitude routinely, without drama, without announcement, as a natural consequence of the magnetic activity that runs through its surface and atmosphere. From Earth, a solar flare arrives as a brief brightening in certain wavelengths and occasionally as disruption to radio communications, as the burst of X-rays and ultraviolet radiation ionizes the upper atmosphere in ways that interfere with signals passing through it. The most powerful solar storm ever recorded happened in 1859. It is called the Carrington event, named after the British astronomer Richard Carrington, who observed the solar flare that caused it and was one of the first people to connect solar activity to events on Earth. The flare was visible to the naked eye, an extraordinarily rare thing for any solar event. Within hours, the effects arrived at Earth. Telegraph systems across Europe and North America failed. Operators reported receiving electric shocks from their equipment. Some telegraph lines continued to transmit messages even after being disconnected from their power sources, running entirely on the current induced by the geomagnetic storm. Auroras, the northern and southern lights, appeared at latitudes where they are almost never seen. People in the Caribbean looked up and saw the sky glowing red and green. Some woke in the night, convinced the sun had risen early. A solar storm of that magnitude today would be a different kind of event. Power grids, satellites, GPS systems, communication networks, all of the infrastructure that modern civilization depends on would be vulnerable. The Carrington event is not ancient history. It is a reminder of what the sun is capable of and a benchmark against which we measure our preparedness for the next large storm. The sun also throws matter into space. Not just radiation, solar flares release energy. But the sun occasionally does something even more dramatic. It releases mass. Enormous bubbles of magnetized plasma, sometimes containing billions of tons of material, are expelled from the corona and launched into the solar system at speeds of up to 3,000 kilometers per second. These are called coronal mass ejections. When a coronal mass ejection is aimed toward Earth, which depends on where the eruption occurred on the sun's surface relative to our position, it can arrive within 1 to 3 days and interact with Earth's magnetic field. The result is a geomagnetic storm. Currents are induced in power lines and pipelines. Satellites in certain orbits experience increased drag. Navigation and communication systems can be disrupted, and the auroras come. The northern lights are the sun touching Earth's atmosphere. This is what they are at their origin. Charged particles from a coronal mass ejection arrive at Earth and are funneled by the planet's magnetic field toward the polar regions. There, they collide with oxygen and nitrogen molecules in the upper atmosphere, exciting those molecules and causing them to release light as they return to their ground state. Oxygen produces the greens and reds. Nitrogen produces blues and purples. The curtains of light that ripple across polar skies on clear nights, the thing that people travel thousands of kilometers to witness, that has been considered sacred or frightening or miraculous by cultures across human history, is the sun's energy redirected by Earth's magnetic field, interacting with air molecules 100 kilometers above the ground. The sun is 150 million kilometers away, and it still manages to paint the sky. Without Earth's magnetic field, the solar wind would strip away the atmosphere. Mars is the example we have closest to hand. Mars once had a magnetic field. It once had a thicker atmosphere. It may once have had liquid water on its surface, rivers, lakes, perhaps an ocean covering a significant portion of its northern hemisphere. And then, billions of years ago, the processes that generated its magnetic field slowed and stopped. The field weakened and eventually disappeared. Without the protection of a magnetic field, the solar wind began to strip the Martian atmosphere away, particle by particle, slowly, over hundreds of millions of years. Today, Mars has an atmosphere about 100 times thinner than Earth's. Its surface is cold, dry, and exposed to radiation levels that would be harmful to any Earth life on the surface. Earth's magnetic field has been protecting this planet's atmosphere for billions of years. It is, in a quiet way, as important to the existence of life on Earth as the Sun itself. The Sun gives. The magnetic field ensures we can keep what we are given. The Sun's influence extends far beyond what we can see. The heliosphere, the vast bubble of space dominated by the Sun's magnetic field and solar wind, extends well beyond the orbit of Pluto. It reaches to a distance of about 100 astronomical units from the Sun, 100 times the distance from the Earth to the Sunday. Within that bubble, the Sun's wind flows outward in all directions, carrying the Sun's magnetic field with it, shaping the environment through which all the planets move. Beyond the heliosphere lies something different: interstellar space. The thin gas and dust that fills the space between star systems, quieter, colder, no longer organized by the Sun's influence. Voyager 1, launched in 1977, and now the most distant human-made object in existence, crossed that boundary in 2012. It is currently more than 23 billion kilometers from Earth, and still the Sun's gravity holds it, still slowing its departure, though it will never return. The Sun reaches further than any other thing in the solar system. Its gravity, its light, its wind, its magnetic field, all of them extending outward into space, long after the planets have been left behind. The Sun does not end at its surface, or at the orbit of Neptune, or even at the edge of the heliosphere. In a very real sense, the Sun extends to the very edge of its own gravitational reach, which means, tonight, wherever you are on this small planet, you are inside the Sunday. The Sun is breathing. Not the way a living thing breathes rhythmically, consciously, in response to need, but in the sense that it is constantly exhaling, constantly releasing something of itself outward into space. A continuous stream of charged particles, mostly protons and electrons, flowing outward from the corona in all directions, at speeds between 400 and 800 kilometers per second. We call it the solar wind. It is not wind the way wind on Earth is wind, a movement of air molecules pushed by temperature differences, something you can feel on your face. The solar wind is plasma, a fourth state of matter, neither solid nor liquid nor gas, but a sea of charged particles moving together under the influence of magnetic fields. You cannot feel it directly. It interacts with the Earth's magnetic field long before it reaches the surface, deflected and redirected by the invisible shield that surrounds this planet. But it is there, right now, flowing past the Earth at hundreds of kilometers per second. The Sun, releasing itself into space, every second, without pause. The solar wind fills the entire solar system, not just the space near the Sunday, not just the inner planets. The solar wind reaches every corner of the solar system past Mars, past Jupiter and its moons, past Saturn and its rings, past Uranus and Neptune, into the cold, dark space beyond the last planet. Everywhere the planets orbit, the solar wind is present. The entire solar system is, in a sense, inside the Sun's atmosphere, inside the region where the Sun's breath is still flowing outward. This is easy to forget when we think of space as empty. The space between planets is not truly empty. It is filled with the Sun's wind, thin beyond anything that would register in everyday experience, but present. A constant flow of charged particles crossing the solar system in every direction, carrying the Sun's magnetic field with it, shaping the environment through which everything moves. Earth's magnetic field is a shield, Without it, the solar wind would reach the surface. The charged particles would interact with the atmosphere differently, stripping away molecules, increasing radiation at ground level, changing the chemistry of the upper atmosphere in ways that would make the surface increasingly hostile to complex life over millions of years. This is not speculation. It is what happened to Mars. Earth's magnetic field, generated by the movement of liquid iron in the planet's outer core, deflects the solar wind, redirecting it around the planet. The wind flows around the magnetic field the way water flows around a stone in a stream. On the side facing the sun, the field is compressed. On the side facing away, it stretches out into a long tail, swept back by the wind. The shape this creates is called the magnetosphere. It is invisible. It has no color, no texture, no surface. But it is there, an enormous, teardrop-shaped region of space dominated by Earth's magnetic field, protecting everything inside it from the full force of what the sun is constantly sending outward. The solar wind does not always arrive calmly. During quiet periods, solar minimum, when sunspot activity is low, the wind is relatively steady and predictable. But when the sun is more active, during solar maximum, the wind becomes more variable. Solar flares send bursts of intense radiation ahead of the wind. Coronal mass ejections send massive clouds of plasma into the solar system, arriving at Earth within 1 to 3 days. When these clouds reach Earth's magnetic field, they compress it on the sunward side and stretch it further on the night side. Currents are induced throughout the system. Energy flows along magnetic field lines toward the polar regions, and in the upper atmosphere, above the poles, something begins to happen that is visible from the ground. The aurora is the solar wind made visible. Charged particles from the solar wind are funneled by the magnetic field toward the polar regions, where the field lines converge and dip toward the surface. There, the particles collide with oxygen and nitrogen molecules in the upper atmosphere, about 100 to 300 kilometers above the ground, and excite them. When those molecules return to their ground state, they release energy as light. Green is the most common color oxygen at lower altitudes, around 100 kilometers up. Red appears at higher altitudes, where oxygen is rarer and the collisions less frequent. Blue and purple come from nitrogen. The specific mix of colors on any given night depends on the altitude of the collisions and the intensity of the storm driving them. The curtains and ribbons of light that move across polar skies, the thing that has stopped travelers in their tracks and brought people to tears, and been woven into the mythologies of cultures across the far north and far south for thousands of years, is the sun redirected. The sun's energy, channeled by a magnetic field, colliding with air, producing light. The sun is 150 million kilometers away. The aurora is its calling card, delivered to the upper atmosphere. The heliosphere is the sun's true size. The visible sun, the disk we see in the sky, the sphere of plasma that produces the light, is about 1.4 million kilometers in diameter. But the sun's actual influence extends far beyond that. The solar wind, flowing outward in all directions, eventually reaches a boundary where its pressure equals the pressure of the interstellar medium, the thin gas and dust that fills the space between star systems. That boundary is called the heliopause. It sits at roughly 120 astronomical units from the Sun, 120 times the distance from Earth to the Sunday, about 18 billion kilometers. The entire region inside that boundary, everything within the Sun's wind and magnetic field, is the heliosphere, a vast bubble of space that the Sun has carved out for itself in the interstellar medium. Inside the heliosphere, the Sun's influence dominates. Outside it, the Sun is just another star. Voyager 1 crossed the heliopause in 2012. It was launched in 1977, more than 40 years before it reached the edge of the Sun's domain. It traveled through the solar system, past Jupiter, past Saturn, past the orbits of Uranus and Neptune, and kept going. For decades, it moved outward through the heliosphere, still inside the Sun's bubble, still carried by the solar wind that had been flowing around it since it left Earth. And then, in August 2012, the instruments on Voyager 1 detected a change. The solar wind dropped dramatically. The density of particles from outside the solar system increased. The magnetic field shifted direction. Voyager 1 had crossed the heliopause, had left the Sun's atmosphere, and entered interstellar space. It is now more than 23 billion kilometers from Earth. It is the most distant human-made object in existence. It is still sending 3 billion back, faint, ancient by the time they arrive, taking more than 22 hours to cross the distance at the speed of light. And it is still moving outward, carrying with it a golden record containing sounds and images from Earth, on the slim chance that something, somewhere, might one day find it. The Sun let it go, but the Sun's gravity still holds it, still slowing its departure, though Voyager will never return. Beyond the heliosphere lies interstellar space. The space Voyager 1 is now crossing is different from the space inside the solar system. It is quieter, colder, no longer organized by the Sun's wind and magnetic field. The particles here came from other stars, from stellar winds and supernova explosions across the galaxy, mixed and thinned over millions of years until they form the diffuse medium between star systems. It is not empty. No part of space is truly empty. But it is emptier than anything inside the heliosphere. A thinner, quieter, older kind of space. The space the Sun has never touched, that no planet of our solar system has ever moved through, that exists between us and the next nearest star as a 4.2 light-year stretch of near-nothingness. Voyager 1 is crossing it now. It will take about 40,000 years to reach the vicinity of the next star system, and it is not aimed at any star in particular. It is simply going outward, into the space between. The Sun was born from interstellar space. The cloud that collapsed to form the Sun 4.6 billion years ago was interstellar medium, the same kind of thin, diffuse gas and dust that Voyager 1 is crossing now. Before the Sun existed, the material that would become it was out there, drifting in the space between stars, seeded with heavy elements from previous stellar generations, slowly cooling, slowly gathering under gravity. The heliosphere is, in a sense, the Sun pushing back against the space it was born from, carving out a territory, maintaining a bubble of its own influence against the slow pressure of the interstellar medium. For 4.6 billion years, the Sun has held that territory, kept its bubble inflated, kept its wind flowing, kept interstellar space at bay beyond the heliopause. And inside that bubble, sheltered from the cold and radiation of interstellar space, life found a way. On a small planet near the inner edge of the habitable zone, under the warmth of a steady star, in the calm at the center of a vast magnetic bubble, something happened that has not, as far as we know, happened anywhere else within reach of our observation. Something woke up, looked around, and eventually lay down on a quiet night and listened to the story of the star that made it possible. The Earth and the Sun have been in a relationship for 4.6 billion years. Not a static relationship, not a fixed distance, a locked orbit, an unchanging arrangement, a living one. The distance between them varies, The angle at which sunlight strikes the surface changes through the year. The amount of energy the sun delivers shifts slightly over long cycles. The Earth responds in its climate, in its seasons, in the long, slow rhythms of glacial periods and warm periods that have shaped the surface of the planet across geological time. We tend to think of the Earth and the Sun as separate things, a planet and a star, object and light source. But they are more entangled than that. The Earth was shaped by the Sun, formed in its presence, warmed by it, protected by a magnetic field generated partly in response to the solar environment. And the Sun, in its small way, has been shaped by the presence of the planets, their gravity tugging on it slightly, their existence a product of the same collapse that produced the star itself. They formed together. They have traveled together through the galaxy for 4.6 billion years. Tonight, as the Earth turns away from the Sun toward darkness, that relationship continues as it has every night since the planet first cooled enough to have a night. The Earth orbits the Sun at an average distance of 150 million kilometers. This distance has a name, 1 astronomical unit. It is the baseline unit of measurement in the solar system, the ruler against which all other distances in our neighborhood are measured. Jupiter is 5 astronomical units. From the Sunday, Neptune is 30. The edge of the heliosphere is roughly 120. The nearest star is about 268,000 astronomical units away. 1 astronomical unit, 150 million kilometers, is the distance that puts Earth in what astronomers call the habitable zone, close enough to the Sun to maintain liquid water on the surface, far enough not to be scorched into a dry, airless world like Venus. The distance is not accidental. It is the result of where, in the disk of gas and dust around the young Sun, the conditions were right for a rocky planet to form and survive. But it is also, by any measure, fortunate. A little closer, and the oceans would have evaporated. A little further, and they would have frozen. The Earth sits in a narrow band of distance around a star where things like oceans and things like us are possible. And it has been sitting there, within that band, for 4.5 billion years. Earth's orbit is not a perfect circle. We are taught to picture the solar system as a neat diagram, planets in clean, circular orbits around a central Sunday. But the reality is more irregular. Earth's orbit is an ellipse slightly elongated, meaning our distance from the Sun changes through the year. In early January, Earth is about 147 million kilometers from the Sunday. In early July, it is about 152 million kilometers away, a difference of about 5 million kilometers. This surprises many people. January, the depth of winter in the Northern Hemisphere, is when Earth is actually closest to the Sunday. July, the height of summer in the Northern Hemisphere, is when we are furthest away. The seasons are not caused by our distance from the Sunday. They are caused by something else entirely. Seasons are caused by the tilt of Earth's axis. The Earth does not orbit the Sun sitting straight up. It is tilted, leaning at an angle of about 23.5 degrees relative to the plane of its orbit. This tilt does not change direction as the Earth goes around the Sunday. The North Pole always points roughly toward the same point in the sky, toward the star we call Polaris, regardless of where Earth is in its orbit. This means that for half of the year, the Northern Hemisphere is tilted toward the Sunday. Sunlight strikes it at a more direct angle. Days are longer. More energy arrives per square meter of surface. It is summer. For the other half of the year, the Northern Hemisphere is tilted away from the Sunday. Sunlight strikes at a shallower angle, spreading across more surface area. Days are shorter, less energy per square meter. It is winter. While the northern hemisphere has winter, the southern hemisphere has summer. The same sun, the same moment, producing opposite seasons on opposite halves of the same planet because of a 23.5-degree tilt that has been present since the early days of the solar system, likely the result of a massive collision between the young Earth and another body during the chaotic early period of planetary formation. The seasons you have experienced your entire life, the cold mornings of winter, the long evenings of summer, are the legacy of a collision that happened 4.5 billion years ago. A total solar eclipse is one of the most extraordinary coincidences in the solar system. The Moon is about 400 times smaller than the Sunday. It is also about 400 times closer to Earth than the Sun is. These two numbers, so different in what they describe, cancel each other out almost perfectly. As seen from Earth's surface, the Moon and the Sun appear almost exactly the same size in the sky. This means that when the Moon passes directly between the Earth and the Sun, which happens occasionally, when the alignment is just right, it covers the Sun's disk almost perfectly. The bright surface disappears. The corona, the Sun's outer atmosphere, normally invisible against the glare of the photosphere, becomes visible. Stars appear in the middle of the day. The temperature drops. Birds go quiet. A total solar eclipse is the consequence of a remarkable coincidence. Two objects of vastly different sizes appearing identical from a particular vantage point, because their distances from that vantage point happen to be in almost exactly the same ratio as their sizes. There is no reason this had to be true. It is not true anywhere else in the solar system. It is not true from Mars or Jupiter or any other planet. It is true from Earth, and only from Earth, because of the specific distance and size of our Moon. This coincidence will not last forever. The Moon is slowly moving away from Earth, drifting outward at a rate of about 3.8 centimeters per year. This is happening because of tidal interactions between the Earth, the Moon, and the oceans, a gradual transfer of energy that has been pushing the Moon into a slightly wider orbit for billions of years. When the Moon was closer early in Earth's history, it appeared larger in the sky than the Sunday. Total solar eclipses would have been even more complete than they are today, the Moon overlapping the Sun's disk with room to spare. As the Moon continues to move away, it will appear smaller and smaller. Eventually, hundreds of millions of years from now, it will no longer be large enough to completely cover the Sun from Earth's surface. Total solar eclipses, as we know them, will end. They will be replaced by annular eclipses, events where the Moon covers the center of the Sun but leaves a ring of sunlight visible around its edges. The sky will not go dark. The corona will not appear. The full strangeness and beauty of a total eclipse will be gone. We are living at the one period in Earth's history when the Moon is exactly the right distance to produce perfect total solar eclipses. Earlier, it was too close. Later, it will be too far. Right now, for this brief window of geological time, we happen to be here. Every day, the Sun rises over a planet it helped create. The elements in the Earth's crust, silicon, oxygen, iron, magnesium, were present in the cloud that collapsed to form both the Sun and the planets. The water in the oceans was delivered partly by comets and asteroids that formed in the outer solar system, in regions shaped by the Sun's gravity. The atmosphere was produced partly by volcanic outgassing over billions of years, driven by heat in the Earth's interior, heat that originated partly from the compression of the planet during its formation from the solar nebula. The Sun did not build the Earth the way a craftsman builds something, but it was present at the beginning. It organized the disk. Its gravity shaped the formation of the planets. Its light drove the chemistry of the early atmosphere. Its warmth has maintained liquid water and therefore life on the surface for nearly 4 billion years. The Sun did not make the Earth, but the Earth would not exist without the Sunday. They are too entangled, too co-produced, too bound up in each other's history to be understood separately. The gravity of the Sun keeps everything in the solar system bound together. Without it, the Earth would travel in a straight line, not a curve, not an orbit, but a straight line outward into space at the speed it currently moves in its orbit, about 30 kilometers per second. In the absence of the Sun's gravity, Earth would cross the distance to Mars in a few months and keep going, eventually leaving the solar system entirely, becoming a rogue planet in the dark between stars. This is true of every planet, every moon, every asteroid and comet and piece of debris in the solar system. All of it is held in place by the gravity of a single star, a star so much more massive than everything else combined that the entire system is, in a very real sense, the Sun's system. The planets are passengers. The Sun is the vehicle and the road and the force that keeps everything from flying apart. Tonight, as you lie still and the Earth turns slowly beneath you, the Sun is 150 million kilometers away, holding this planet in its orbit the way it has held it for 4.5 billion years, gently, continuously, without effort or intention, just gravity doing what gravity does. The light that enters your eyes at sunrise has traveled 150 million kilometers to reach you. It left the surface of the Sun 8 minutes and 20 seconds before it arrived at your eyes. It crossed the vacuum of space at 300,000 kilometers per second, the fastest speed anything in the universe can travel. It passed through the Earth's atmosphere, was scattered and filtered and diffused by air molecules and water droplets, and arrived at your eyes as the first light of a new day. This happens every morning. It has happened every morning since the Earth first had mornings. It will happen every morning for billions of years after this one. The Sun rises, and light that was inside a star 8 minutes ago enters the eyes of the creatures living on the planet. The star is warming. It is ordinary. It happens every day. Most mornings, you probably did not think about it. But tonight, lying in the dark that the Sun left behind when it passed over the horizon, you know what it actually is. You know where it came from. You know the journey it made to reach you. And tomorrow morning, when the light comes again, you will know it for what it is. The Sun arriving, as it always has, as it always will. The Sun is ordinary. This is not an insult. It is one of the more interesting things about it. In a universe containing hundreds of billions of galaxies, each containing hundreds of billions of stars, the Sun is by almost every measure astronomers use to classify stars completely, unremarkably average, middle-aged, middle-sized, middle brightness, neither the hottest nor the coolest, neither the largest nor the smallest, neither the youngest nor the oldest. If you were cataloging stars the way a librarian catalogs books, the Sun would go in the middle of the middle shelf. Nothing about it would make you stop and look twice. And yet, from where we stand, there is nothing ordinary about it at all. From where we stand, it is the center of everything, the source of all light, the keeper of all orbits, the reason anything on this planet is alive. Ordinariness, it turns out, is relative. There are approximately 300 billion stars in the Milky Way. 300 billion. The number is large enough that it stops being a number in any practical sense and becomes more like a direction, a gesture towards something too large to hold. If you spent 1 second looking at each star in the Milky Way, the process would take nearly 10,000 years. If you tried to count them at 1 per second, you would need to start counting before the pyramids were built, and you still would not be finished today. The sun is one of those 300 billion, one point of light among hundreds of billions of points of light, all of them burning, all of them with their own planets and their own histories and their own long futures stretching ahead of them. The sun is not special in this company. It is simply one of the crowd, and yet it is the only one close enough to warm your skin. About 85% of stars in the Milky Way are smaller and dimmer than the Sunday. This surprises many people. We tend to think of the sun as average, and it is, in a rough sense. But the distribution of stellar sizes in the galaxy is not a smooth bell curve centered on the Sunday. Most stars are smaller, red dwarfs, cool, dim, long-lived stars with a fraction of the sun's mass and luminosity are by far the most common type of star in the galaxy. They are so dim that not a single one is visible to the naked eye from Earth, despite being our nearest stellar neighbors. Proxima Centauri, the closest star to the Sun, at 4.24 light-years away, is a red dwarf. It is about 1/7 the diameter of the Sun and produces only about 0.17% as much light. If you replaced the Sun with Proxima Centauri, keeping Earth at the same distance, the sky would be orange-red and the light would be dim, less than 1,000th of what we receive today. Plants might struggle. The Earth would cool significantly. We are fortunate to orbit a star as bright and warm as the Sunday. Most planets in the galaxy orbit something considerably dimmer. But some stars make the sun look like a candle. At the other end of the scale, the far, extreme end, are the stars that challenge the imagination in the opposite direction. Massive, luminous, burning through their fuel at rates that make the sun's 4 billion-year remaining lifespan seem conservative. UY Scuti is one of the largest known stars. It is a red supergiant located about 9,500 light-years from Earth, so far away that it is completely invisible to the naked eye, despite being almost incomprehensibly large. Its radius is approximately 1,700 times that of the Sunday. If placed at the center of the solar system, its surface would extend past the orbit of Jupiter. Jupiter, the largest planet, a world so large that all the other planets in the solar system could fit inside it, would be swallowed by UY Scuti's atmosphere. The Earth would not be near the surface. It would be deep inside the star. Standing next to UY Scuti, the Sun is a small, quiet, completely unremarkable point of light. But size is not everything. Longevity matters too. The most massive stars burn brightest and die youngest. A star 20 times the mass of the Sun burns through its hydrogen fuel in a few million years, then dies in a supernova explosion, scattering its contents across the galaxy. Beautiful, violent, brief. The Sun will burn steadily for another 5 billion years. Red dwarfs, the small, dim stars that make up the majority of stellar population in the galaxy, will burn for tens or even hundreds of billions of years. Some red dwarfs have lifetimes longer than the current age of the universe. They are so efficient with their fuel, so careful in their burning, that they will still be shining long after the Sun has expanded into a red giant and shed its outer layers into space. Life, as we know it, requires time. It took nearly 4 billion years for complex, multicellular life to evolve on Earth. It took another 500 million years for life capable of looking up at the stars and wondering about them. A star that burns for only a few million years does not give life enough time. A red dwarf that burns at very low levels may not provide enough energy. The Sun burning steadily at the right temperature for billions of years sits in a range that seems to be compatible with the emergence of complexity. Whether this is a coincidence or a requirement is a question we do not yet have enough examples to answer. The nearest star to the Sun is Proxima Centauri, 4.24 light-years away. 4.24 light-years. The light from Proxima Centauri takes 4 years and 3 months to reach us. If you could travel at the speed of our fastest spacecraft, the New Horizons probe, moving at about 58,000 kilometers per hour, the journey to Proxima Centauri would take approximately 78,000 years. 78,000 years at the fastest speed humanity has ever achieved. The nearest star, the closest one, not across the galaxy, just next door by galactic standards. And it would take 78,000 years to reach it at our current best. Space is not mostly things. Space is mostly space. If the Sun were the size of a soccer ball, Proxima Centauri would be another soccer ball about 5,000 kilometers away. To put that in context, 5,000 kilometers is roughly the distance from London to New York. 2 soccer balls, one in London, one in New York, with nothing but empty space between them. That is the scale of the distance between the 2 nearest stars. Scale the rest of the galaxy to match, and the Milky Way would be a disk about 100 million kilometers across roughly the distance from the Earth to the Sun in real scale. The stars in our galaxy are not packed close together. They are islands in an ocean so vast that the ocean is almost entirely ocean. The light we see on clear nights, that crowded, glittering sky, is an illusion created by the extraordinary distances involved. Those stars are not neighbors. They are separated by distances that make the gap between Earth and the Sun look like a short walk. Every star you have ever seen with the naked eye is in our own galaxy. Not just in our own galaxy, in our own small neighborhood of the galaxy. The most distant star visible to the naked eye under ideal conditions is about 16,000 light-years away. The Milky Way is about 100,000 light-years across. The stars we see on the clearest night are a tiny sample of the nearest stellar population, a small, local neighborhood in a galaxy of 300 billion stars. The rest, the vast majority of the stars in the Milky Way, and all the stars in every other galaxy, are beyond the reach of unaided human vision. They exist. They burn. They may have planets. Some of them may have planets with living things on them, looking up at their own sky, seeing their own small sample of their own galaxy. We do not know. We are working on finding out. The Sun will outlive almost everything we have ever built. The oldest human structures still standing, the pyramids, the ancient stone circles, the ruins of the earliest cities, are a few thousand years old. The oldest written records go back perhaps 6,000 years. Human civilization, in any recognizable form, is perhaps 10,000 years old. The Sun will burn for another 5 billion years. 5 billion years from now, there will be nothing left of anything we have made. The continents will have rearranged themselves beyond recognition. The species alive on Earth today, including ours, will be gone, replaced by whatever evolution produces over 5 billion years of selection pressure. The oceans may still be there, though they will be warmer as the Sun slowly brightens. The sky will still be blue. The Sun will still rise every morning over whatever lives beneath it. And 5 billion years from now, the Sun will still have been burning for longer than we can think about, and will still have an ending ahead of it. The Sun is the most studied object in the history of science. No other object has received more sustained, more detailed, more varied attention from human observers than the Sunday. from ancient astronomers tracking its movement across the sky, to Galileo observing sunspots through an early telescope, to the fleet of satellites currently monitoring it in real time across multiple wavelengths simultaneously. The Sun has been watched, measured, photographed, and analyzed more thoroughly than anything else we can point an instrument at, and it still surprises us. The mystery of the corona's temperature, the not fully understood mechanisms of sunspot cycles, the behavior of solar flares in their finest detail, the precise way the heliosphere interacts with the interstellar medium. Questions that remain open despite centuries of observation and decades of space-based monitoring. The nearest, brightest, most observed star in the universe, and it is still teaching us things we did not know, still revealing layers we had not suspected, still, in its ordinary, everyday burning, being more complex and more interesting than anything we have yet fully understood. The Sun has been watched for all of human history, and we are still learning to see it. In 5 billion years, the Sun will run out of hydrogen. Not all at once, not suddenly. Stars do not switch off the way a light bulb does a sudden darkness, a filament burning out, the room going black. The transition will be slow by any human measure, though fast by the standards of geological time. Over millions of years, the hydrogen in the core will become depleted. The balance between the outward pressure of fusion and the inward pull of gravity, the balance that has kept the Sun stable for 4.5 billion years, will begin to shift. The core, no longer producing enough energy to support the weight of the layers above it, will begin to contract. It will grow denser, hotter, and the increased heat will cause the outer layers of the Sun to respond in the opposite direction, expanding outward, slowly, over millions of years, into a vastly larger, cooler, redder version of the star it once was. The Sun will become a red giant. The red giant's sun will be almost unrecognizable. Today, the Sun is 1.4 million kilometers in diameter, large enough to contain 1 million Earths, and yet compact enough that the light from its surface takes only about 2 seconds to cross from one side to the other. As a red giant, its diameter will expand to somewhere between 100 and 200 times its current size. Its surface, which today is 5,500 degrees and blindingly bright, will cool to perhaps 3,000 degrees and will glow a deep, dull red. From Earth, if Earth still exists in a recognizable form, the sky will look nothing like it does tonight. The Sun will fill a significant portion of the sky, not as the small, fierce disk we know as an enormous, dim, rust-colored presence covering a large arc of the horizon. The light will be different. The warmth will be different. The shadows will be different. Everything about the experience of living under a star will have changed. Mercury and Venus will be consumed. As the Sun expands into its red giant phase, the innermost planets will not survive. Mercury, already the most scarred and battered planet in the solar system, with virtually no atmosphere to protect it, will be engulfed first, swallowed by the expanding outer layers of the Sun without ceremony. Venus will follow the planet that is in some ways most similar to Earth in size and composition, now gone, absorbed into the star it has orbited for billions of years. What happens to Earth is less certain. Some models suggest the Earth will also be engulfed, that the expanding Sun will grow large enough to swallow the orbit of the third planet as well. Other models suggest that Earth will survive, pushed into a wider orbit by the Sun's loss of mass during the red giant phase, ending up as a scorched, airless rock at a greater distance from the dying star. Either way, the Earth as it exists tonight with its oceans and atmosphere and thin layer of life covering its surface will not survive. The oceans will have boiled away billions of years before the red giant phase even begins, as the sun slowly brightens over the next billion years. Life on the surface, if it still exists by then, will have to have retreated deep underground or into the oceans, and eventually will have to leave entirely or cease to exist. 5 billion years is a very long time. Whatever lives on Earth in 5 billion years, if anything does, will not be us. It will be something we cannot imagine, the product of 5 billion years of evolution beyond what we are now. But the end of the sun is not the destruction of everything. This is important. The death of a star is not simply an ending. It is also, in a very real sense, a beginning. As the sun expands into a red giant, it will shed its outer layers, blowing them outward into space in a slow, expanding shell of gas. This shell, illuminated by the hot core left behind, will glow. It will be visible from great distances as a cloud of glowing gas surrounding a bright central point. We call this a planetary nebula. The name is misleading. It has nothing to do with planets. It is an artifact of early astronomy, when these objects were first observed through small telescopes and their round, glowing shapes reminded observers of planets. What they actually are is the discarded outer layers of a dying star, the sun's last breath, expanding slowly into space. The material in that shell, hydrogen, helium, carbon, oxygen, and the other elements produced during the sun's life will drift outward for thousands of years, thinning and cooling, eventually becoming part of the interstellar medium, part of the raw material from which future stars and future planets will form. The sun will die, and in dying, it will seed the galaxy with the material for new suns. At the center of the planetary nebula, the core of the sun will remain, stripped of its outer layers, compressed by its own gravity to roughly the size of the Earth. The core will become a white dwarf, a dense, hot remnant glowing not from fusion but from residual heat. There will be no more fusion. The white dwarf does not burn. It simply radiates away the heat it accumulated over billions of years of active stellar life, cooling slowly, over billions of years more. A white dwarf, the mass of the sun packed into a sphere the size of the Earth. The density is extraordinary. A teaspoon of white dwarf material would weigh several tons. The gravity at the surface is about 350,000 times stronger than the gravity you are experiencing right now, lying still. A human being on the surface of a white dwarf, if such a thing were possible, would weigh about 25 million kilograms. It is one of the strangest objects in the universe, and the sun will become one. White dwarfs cool over billions of years. The process is slow in a way that makes even stellar timescales seem brief. A white dwarf cooling from its initial temperature of tens of thousands of degrees to something close to the temperature of the background universe will take longer than the current age of the universe, longer than the Patchworld, 13.8 billion years that have already passed since the Big Bang. Astronomers have predicted that white dwarfs will eventually cool, completely becoming cold. Dark objects, called black dwarfs. Objects that no longer emit any significant radiation, that have become, for all practical purposes, dead stars, drifting silently through the galaxy. But here is the thing. The universe is not old enough yet for any black dwarf to exist. Every white dwarf that has ever formed, from every star that has ever died in the history of the universe, is still warm, still glowing, still cooling, but not yet cold. The universe has not had time for even a single star to complete that final transition. The sun, when it becomes a white dwarf in about 7 billion years, will join a population of stellar remnants that are all still in the early stages of a cooling process measured in trillions of years. The material the sun sheds will become part of new stars. This is the thought to hold as the sun's future settles into you. The carbon the sun has been producing in its core, the oxygen, the elements that have been building up through the long, slow chemistry of stellar nucleosynthesis over 4.5 billion years. When the sun sheds its outer layers in the red giant and planetary nebula phases, that material will be released into the interstellar medium. It will drift. It will cool. It will mix with the gas and dust already out there, the remnants of other stars that have died at other times, seeding the galaxy with their contents. And eventually, somewhere, over millions or billions of years, gravity will pull some of that material together. A new cloud will collapse. A new star will ignite. New planets will form from the disk of leftover material orbiting the young star. And some of those planets may have the right conditions, the right distance from their star, the right chemistry in their oceans, the right amount of time. The sun's death will contribute in some small way to the conditions that make the next generation of worlds possible. The material that is now inside the sun, that has been inside the sun for 4.5 billion years, will go on, will become part of something new, will not be wasted. The sun does not end, it transforms. This is the final thought on the sun's future. Not an ending, but a transformation, from a main sequence star to a red giant, from a red giant to a planetary nebula, from the outer layers of a planetary nebula to the interstellar medium, from the interstellar medium to new clouds and new stars and new planets. The core left behind cools slowly into a white dwarf, then eventually into a black dwarf, then drifts through the galaxy as a cold, dark remnant for longer than the current age of the universe. Nothing is lost. The mass is conserved. The elements persist. The matter that is the sun tonight will still be matter in different arrangements, in different places, doing different things, long after the star itself has changed beyond recognition. Matter does not end. It changes form. It moves through the universe, from one arrangement to another, from one star to another, from one world to another, following the laws of physics that have been running since the Big Bang and will keep running long after the sun is gone. The sun will end, and everything it was made of will continue, just as everything you are made of will continue long after the particular arrangement that is you has dissolved and returned to the world, and the world has returned to the star, and the star has returned to the space between stars, and the space between stars has gathered again into something new. Nothing ends. It only changes. And change, in a universe like this one, is how the story keeps going. The energy keeping you alive right now came from the Sunday, not in a general sense, not as a distant, abstract connection between a star and a planet, in a direct, physical, traceable sense. The energy your heart is using to beat right now, as you lie, still came from food. The food came from plants, or from animals that ate plants, or from animals that ate animals that ate plants. The plants grew by capturing sunlight, by absorbing photons from the sun, and using their energy to assemble carbon dioxide and water into sugar. That sugar is stored chemical energy, stored sunlight. The energy moving through your heart right now was, not long ago in the grand scheme of things, a photon leaving the surface of the Sunday. It crossed 150 million kilometers of space. It entered the atmosphere. It hit a leaf. It was absorbed. It was converted into chemical energy and stored in the molecular bonds of a sugar molecule. It moved through the food chain, through whatever path it took from leaf to the thing you last ate. And then, your body broke those bonds open and used the energy they contained to power everything that keeps you alive. The sun is not just outside, it is inside, running through you, keeping you warm, keeping you here. Every breath you take is a gift from the Sunday. The oxygen in the air, the oxygen your body is extracting from each breath right now, quietly, without effort, was put there by photosynthesis. By billions of years of plants and algae and photosynthetic bacteria using sunlight to split water molecules, releasing oxygen as a byproduct. The oxygen in Earth's atmosphere was built up, molecule by molecule, over nearly 3 billion years, by living things using the energy of sunlight to do chemistry. Before photosynthesis, Earth's atmosphere had almost no free oxygen. It was nitrogen, carbon dioxide, and small amounts of other gases. The transformation of the atmosphere from oxygen-poor to oxygen-rich is the single largest chemical change the Earth's surface has ever undergone. And it was done by living things, using sunlight, over billions of years. Every breath you take is the product of 3 billion years of solar-powered chemistry. The carbon in your body was assembled by the Sunday. Your body is mostly water, but the structural material, the proteins, the DNA, the cell membranes, the complex molecular machinery of a living thing is built primarily from carbon. Carbon chains, carbon rings, carbon atoms, bonded to hydrogen and nitrogen and oxygen in configurations of extraordinary complexity. That carbon was in the air as carbon dioxide. Plants absorbed it, using sunlight to break the carbon dioxide apart and keep the carbon, building it into the structures of their tissues. When you ate directly or indirectly, you consumed that carbon. Your body dismantled the structures it arrived in and reassembled the carbon into your own molecules. The carbon atoms in your body were assembled into organic molecules by sunlight. They were taken from the air by plants responding to sunlight. They were incorporated into your body through the chain of eating and being eaten that connects every living thing to every other living thing. And at the base of that chain, always, is a photon and a leaf. The warmth in your body is stored sunlight. You are warm right now. Not as warm as you might be lying still in the dark. The body's temperature regulation has shifted into a quieter mode. But warm. The heat in your tissues, the specific temperature that distinguishes a living body from its surroundings, is the product of metabolic processes of chemical reactions occurring in every cell, releasing energy as heat. That energy came from food. The food came from the Sunday. The warmth you feel in your own body, the warmth that tells you that you are alive, that distinguishes you from the cool air around you, is sunlight that was converted into chemical energy and then into heat through the process of living. You are carrying the sun's warmth inside you tonight. You have been carrying it your entire life, renewed with every meal, maintained by every metabolic process in every cell. The sun warms the world from 150 million kilometers away, and it warms you from inside. Without the sun, the Earth would be silent and frozen within weeks. We have already visited this fact, but it is worth returning to from a personal angle. Without the sun, the surface temperature of the Earth would average around -18 degrees Celsius within a year. The oceans would begin to freeze. The atmosphere would cool. The water cycle would stop. Rain would stop. Rivers would stop. The food chain would collapse, first the photosynthesizers, then the animals that depend on them, then everything else, in a cascade of extinction that would leave the surface of the planet cold and still and dark. Nothing you know, nothing you have ever seen or touched or eaten or loved would survive the absence of the sun for very long. You are not just living on a planet warmed by a star. You are dependent on that star for every aspect of your existence: the food, the air, the warmth, the water cycle, the magnetic protection, the light that enters your eyes and tells your brain what time of day it is, what season it is, when to sleep and when to wake. The sun is not background. It is not scenery. It is the reason everything you have ever known exists. You are a creature of the Sunday. This is not metaphor. It is description. You are made of elements forged in stars, carbon and oxygen, and iron assembled in stellar furnaces and scattered into space by stellar explosions. You are powered by the energy of the nearest star, converted into food by plants, moving through your body as the warmth of a living thing. You breathe an atmosphere built by 3 billion years of solar-powered photosynthesis. You see by sunlight. Your sleep cycles are regulated by the sun's daily passage across the sky. Your seasons are determined by the sun's angle. Your climate is maintained by the sun's warmth. You did not come from the sun directly. You came from the earth, from the food chain, from the long history of life on this planet. But the earth itself came from the sun's neighborhood, from the disk of material surrounding the young sun 4.5 billion years ago. And life on Earth has been running on sunlight since almost the beginning. Trace anything about you back far enough, and you arrive at the Sunday. The light entering your eyes at the moment you wake tomorrow will have traveled 150 million kilometers to reach you. It left the surface of the sun 8 minutes before it arrives at your eyes. It crossed the vacuum of space at the maximum speed the universe permits. It entered the atmosphere, was scattered and softened by air and water vapor, and arrived as it arrives every morning, as it has arrived every morning for 4.5 billion years, as the first light of a new day. You will probably not think about this when it happens. You will probably register the light as a signal to wake, to begin, to re-enter the day. And that is exactly what it is. A signal from a nuclear furnace 150 million kilometers away, telling a small living thing on a small planet that another day has begun. The most ordinary thing in the world, the most extraordinary thing in the world, both at the same time. The sun has been rising over this planet for 4.6 billion years. It rose over the first oceans before there was anything alive in them. It rose over the first photosynthetic bacteria, which began, slowly, to change the atmosphere. It rose over the first fish, the first amphibians, the first forests. It rose over the dinosaurs for 165 million years. It rose over the first mammals, the first primates, the first humans. It rose this morning over you, and tomorrow it will rise again, as it has every morning since the earth had mornings, over whatever is alive and awake and looking up at the brightening sky. The sun does not know we are here. It does not know that anything is alive on the third planet of its system. It does not know that some of the creatures living there have, in the last few centuries, begun to understand what it actually is, a nuclear furnace, 4.5 billion years old, converting hydrogen into helium and light and warmth in a process that will continue for another 5 billion years. It simply burns, as it has always burned, patient and vast and indifferent in the way only a star can be. And underneath it, on the small planet, it warms things live, things breathe, things wonder about the star they live beneath. And sometimes, late at night, they lie still in the dark and listen to the story of the fire that made them. You are resting in the dark, the sun left behind, When the sun passed over the horizon tonight, when the last light faded and the sky deepened into the blue-black of night, it did not disappear. It moved. It is on the other side of the earth right now, rising over other oceans, warming other mornings, filling other skies with light. It is doing what it has always done, unchanged by the fact that you cannot see it. The darkness you are resting in is not the absence of the Sunday. It is simply your side of the planet turned away from it. The sun is still there, still burning, still holding this planet in its orbit, still warming the side of the Earth that faces it, still sending its wind through the solar system, its light across 150 million kilometers of space, its warmth into the atoms and molecules and living things on the surface of a small, rocky world that owes it almost everything. You are not separate from the sun tonight, simply because it is dark. You are carrying its warmth in your body. You are breathing the atmosphere it helped create. You are resting on a planet held in place by its gravity, protected by a magnetic field generated in response to its presence. The sun is everywhere tonight. It is just quiet, and tonight the sun is 150 million kilometers away, burning as it has always burned. And you are here, on the planet it made, breathing the air it filled, warm with the energy it sent, resting in the dark it left behind. Close your eyes. The sun will rise again in the morning. It always does. There is a star 150 million kilometers from where you are lying right now. You cannot see it tonight. It is on the other side of the world, doing what it has always done, rising over other oceans, warming other mornings, filling other skies with the light that has been filling skies on this planet for 4.5 billion years. It does not know you are here. It does not know anything is here. It simply burns, as it has always burned, patient and vast and indifferent in the way that only something 4.5 billion years old can be. And yet everything about the moment you are in right now traces back to it. The warmth in your body tonight is the Sunday. Not the sun as a distant object in the sky, the sun as energy, transformed and carried through the food chain, stored in the chemical bonds of the molecules that fuel your cells, released as heat by the metabolic processes running quietly through your body as you lie still. The warmth that tells you that you are alive, that distinguishes a living body from the cool air around it, is sunlight, converted and stored and carried here through the biology of everything that came between you and a leaf in sunlight. You have been carrying the sun inside you your entire life, renewed with every meal, maintained by every breath, kept alive by processes that trace back in an unbroken chain to a photon that left a nuclear furnace 150 million kilometers away. The air filling your lungs right now was made by the Sunday, not directly but through the long, patient work of 3 billion years of photosynthesis. 3 billion years of plants and algae and bacteria using sunlight to split water molecules and release oxygen into the atmosphere, molecule by molecule, slowly transforming an oxygen-poor world into the world you breathe. The atmosphere you depend on for every breath, the thin layer of gas that separates living things from the vacuum of space, was built by living things, using sunlight over a span of time that makes all of human history look like an afternoon. Every breath you take tonight is the product of 3 billion years of solar-powered chemistry. The sun built the air you are breathing right now. It has been building it since before there was anything on this planet complex enough to breathe it. The ground beneath you was made by the Sunday. not directly, but through the disk of gas and dust that surrounded the young sun 4.5 billion years ago, the material that did not fall into the star, that swirled and collided and slowly accumulated into the rocky inner planets. The Earth assembled itself from the leftovers of the sun's formation. The silicon in the rock beneath you, the iron at the planet's core, the water in the oceans that makes up most of your body. All of it present in the cloud that collapsed to form the solar system organized by the sun's gravity, shaped by its presence, carried into the orbits that define the solar system we live in. You are not resting on a planet that happens to orbit a star. You are resting on a planet that formed alongside a star, from the same cloud of ancient gas and dust, bound to it by gravity since before the Earth had cooled enough to have a solid surface. The darkness around you tonight was made by the sun too. This is the strangest thing. The night, the dark, the quiet, the cool stillness that allows sleep exists because the Earth is a sphere, and a sphere can only face one direction at a time. The side facing the sun has day. The side turned away has night. The darkness you are resting in is not the absence of the Sunday. It is the geometry of a planet, the simple fact that a sphere rotates and the side facing away from the light has darkness. The night is the sun, seen from its shadow. And in that shadow, on this planet, something evolved to rest, to close its eyes, to let the busy, daylight-driven processes of a body slow and consolidate and repair. Sleep is a creature of the night, which means sleep is a creature of the sun, shaped by the rhythm of a rotating planet around a star, calibrated over millions of years of evolution to the 24-hour cycle of light and dark that the Earth's rotation produces. You are sleeping because the Earth turns. The Earth turns because the sun's gravity holds it in orbit. You sleep because of the Sunday. Tonight, as you lie still, the sun is on the other side of the world. It is rising over the Pacific Ocean right now, the first light touching the surface of the water, the sky going from black to deep blue to the pale gold of early morning. Somewhere, someone is watching that sunrise. Somewhere, something is waking, a bird calling in the early dark before the light arrives, a flower beginning to open as the temperature rises, a tide of biology stirring in response to the signal that has been arriving every morning for 4.5 billion years. The sun does not rest, it does not slow, it does not pause to notice that half the world is sleeping while the other half is waking. It simply burns, continuously, pouring energy in every direction, warming everything within range, holding everything in orbit, filling the solar system with its wind and its light and its patient, constant presence. It has been doing this since before the Earth had oceans. It will be doing this long after everything alive on Earth tonight has been replaced by things we cannot imagine. And in 5 billion years, it will change. The hydrogen in its core will run low. The balance that has kept it stable will shift. It will expand, slowly, into something vast and red and cool, a red giant that fills a significant portion of the sky from wherever anything is still alive to see it. Its outer layers will drift away into space, glowing, becoming the kind of beautiful, ephemeral cloud of gas we see when we look at other dying stars through telescopes. The core will remain compressed into a white dwarf, cooling slowly over billions of years. The material shed by the dying sun will drift through the galaxy and eventually become part of new clouds, new stars, new planets. The sun's death will seed the galaxy with the elements it spent its life assembling. Nothing will be lost. Everything will continue. just in different forms, in different places, doing different things the way matter has always moved through this universe, from one arrangement to another, from one star to another, from one world to another. The sun does not end, it transforms, and what it leaves behind, the carbon, the oxygen, the elements forged in its interior and scattered into space, when it dies, may one day become part of something new, part of a new star, part of a new planet, part of something that has not yet been imagined, that will arise in conditions we cannot predict, in a future so distant it has no meaning in human terms. The sun has been making things possible for 4.5 billion years. Its death, when it comes, will be another act of making another contribution to the long process by which the universe builds complexity from simple beginnings, scatters it into space, and gathers it again into new forms. This is what stars do. This is what the sun has always been doing. Not just warming a planet, building towards something, contributing to the process, playing its part in the long, slow story of a universe learning to make things more interesting than hydrogen. Tonight, lying still in the dark, you are the most interesting thing the sun has yet produced. Not because you are the end of the process. The universe is 13.8 billion years old, and the sun has 5 billion years left to burn. There is vastly more story ahead than behind. But in this moment, in this particular arrangement of matter, a body warm, with stored sunlight, breathing air built by 3 billion years of solar-powered photosynthesis, resting on a planet shaped by the sun's formation, something is happening that, as far as we know, has not happened many places in the universe. Something made of stardust is thinking about the stars. Something warmed by a nuclear furnace 150 million kilometers away is lying in the dark, wondering what that furnace actually is. Something assembled by the sun is listening to the story of the sun and feeling, somewhere beneath the thinking, something that might be called wonder. The sun does not wonder, it burns. It is the wondering that is new, the wondering that is rare, the wondering that is, as far as we know, the most extraordinary thing this solar system has ever produced. So let the wonder settle now. Let it soften into something quieter. The sun is burning on the other side of the world. It will rise again in a few hours, as it has risen every morning since the earth first cooled enough to have mornings. It will warm the air. It will feed the plants. It will drive the weather. It will fill the sky with the scattered blue of morning, and you will wake beneath it, warm, breathing, alive with its energy, resting on the planet it shaped, protected by the magnetic field it helped generate, sustained by the food chain it powers, breathing the atmosphere it helped build. You are a creature of the Sunday. You have always been a creature of the Sunday. And tonight, in the darkness the sun left behind when it passed over the horizon, you are resting, as you were designed to rest. As every living thing on this planet has rested since before there was anything on this planet complex enough to sleep. Let the breathing slow. Let the body grow heavy. Let the thoughts soften into something wordless and warm. The sun is on the other side of the world. It is burning as it has always burned. And you are here, in the dark it left behind, warm with its energy, breathing its air, resting on its planet. Close your eyes. It will be back in the morning. It always comes back. Good night.